You know, in chemistry, when we teach a lot of concepts, we have to introduce a lot of new terminology, and students often say, you know, it's all Greek to me because they've never heard of words, you know, stoichiometry, what's that? And so that's one thing that we deal with, but also we deal with having to use terms in a more precise way in chemistry or in science than we use them in our daily lives. And that presents its own difficulty or misconception for students. And one of the most prevalent misconceptions for students, and things that we have to overcome when we teach them, is the difference between heat and temperature. Now, why is that confusing to students? Well, because in our daily lives, when we go about things, we think if something is hot, it has a high temperature, so we tend to use those terms almost interchangeably. But in fact, they're very different. And when you study thermochemistry, you need to be able to distinguish them and understand that difference. Now, you can illustrate, if you wanted to, the difference between heat and temperature. If I had some boiling water here, and imagine that I've got a pot of boiling water, a large pot, and if I took a drop of that boiling water and I put it on my hand, it would hurt, but it wouldn't be a catastrophe. If, on the other hand, I took a pot of boiling water and I poured it on my hand, that would be a trip to the emergency room. What's the difference? Well, the difference is not the temperature. It's the same pot of boiling water. It's all at 100 degrees Celsius. The difference is the amount of heat energy that is in there. So this demonstration is to give a colorful analogy for my drop of boiling water versus a pot of boiling water. What I've got are 3 beakers with different amounts of water. I have 100 milliliters of water, 400, and 800 milliliters of water. And my heat is going to be this purple concentrated solution. Actually, it's a very, very dilute solution of potassium permanganate, just to give a purple color. And I'm going to add the same amount of heat to each beaker. And what I'm going to try to see is what is the relative temperature of the water in each beaker. And so you could ask them, do you think the temperature would be the same for all of these beakers with the water in them if I add the same amount of heat to each? So you could ask students to predict that. And the amount of heat that I'm going to add is 2 drops of heat, because that's how we measure heat. So I'm going to go ahead and very carefully add 2 drops of heat to the first, 2 drops of heat to the second, and 2 drops of heat to the third. And the question is, if that's my heat, if that I just added was the analogy for the heat, then what is the temperature going to be? And I'm going to stir these just so that we can mix that food coloring. Right now we just have a demonstration of diffusion. And what I'm going to do is put a whiteboard behind that so that you can focus on the color intensity. If the amount that I added there, 2 drops, was a constant amount of heat energy added, transferred to each beaker of water, what is the resulting temperature of the water? Well, what's my analogy? The analogy for the temperature now is the color intensity. So I'm going to go up here so that I can see the colors as well. And I think you can see that there's a difference in the color if you look straight on, that is perpendicular to the beakers. Okay? You don't want to look from the top down because you've got different volumes. But if you look this way through each, then your path of light is the same in each. Okay? And so we see that there's qualitatively, and this is a qualitative analogy, a different color intensity. We have a fairly nice, very pretty violet purple color there, a little bit lighter, not as deep a color, and you can see a definite difference here where it's much lighter than the first 2, and even between the second and the third. So what's different here is the temperature. Now, it's very difficult, as it turns out, to give a good definition of temperature. And that's a problem. Sometimes, what is temperature? Well, it's a quantitative measure of heat and energy and so on. But probably the best way to define temperature is to say that heat transfer always occurs from higher temperature to lower temperature. And that if two things are in thermal equilibrium and there is no net heat transfer, then they must be at the same temperature. And believe it or not, that's probably the best definition of temperature, is that if two things are at the same temperature, no heat can be transferred between them. So this is called colorful heat. It's simply a colorful analogy for the difference between heat and temperature. Now, you could extend this a little bit further, and you could use the heat-energy equation, and you could say, well, I had different amounts of water, so obviously the the heat transferred is going to depend on the temperature difference that we get. It's going to depend on the mass of the substance being heated, in this case the water, and it's going to depend on something called the specific heat or heat capacity, and since we had water, which is the nature of the substance, we have the same substance in each. You could ask yourself, well, how could I get beakers 2 and 3 to have the same temperature? I added 2 drops of heat to each beaker, but I have twice as much water in beaker number 3. So you would ask your students to predict, how much more heat would I have to add to beaker number 3 to get the same temperature that is the same color intensity in 2? And I think your students would probably say, well, let's add twice as much heat, right? Because here I had 400 milliliters and I got 1 temperature. Here I had 800. I got a lower temperature because it wasn't as dark. So I'm going to go ahead and add 2 drops of heat to beaker number 3 to see whether we can get the same temperature in beaker number 3 as we have in beaker number 2. And so I add 2 drops there. And I'm going to go ahead and stir one more time. And now again, what we want to do is compare the color where you're looking perpendicular to the beaker to see whether the color intensity is the same in beaker 2 and 3. And, oh yeah, that looks pretty good to me. If you compare the color in 2 and 3, that looks like exactly the same color, the exact same temperature. So I had to add twice as much heat because I had twice as much material to get the same temperature. You could use this even when you do calorimetry and you talk about, the heat-energy equation and so on. Thank you.